As I said yesterday, all of these integrations really are just one of two situations. Integration by substitution and integration by parts. Now, we talked a bit about substitution in extension 1, but let's look at it again and introduce what I call the non-standard integrals. So they do not appear on the reference sheet, but by geez, they're handy to remember because it's going to save you a lot of time. Du on root u. It comes up so often in our questions. Integrate du on root u and you get 2 root u. Okay, you don't have to worry about putting them back in the index form and all that. Bang, there's the answer. This one also comes up a lot. Du on u squared, just minus 1 on u. Log. Now log, this you actually do work out by integration by parts, but again, it's something that comes up so much, you just remember it. Log x, integrate it, you get x log x minus x. Tan, we've talked about that one. I put down the log of sec. Of course, if you prefer, you could have minus the log of cos. I mean, I prefer doing it that way. Sectan and these other two. They used to be on the old reference sheet. For some reason, when they created the one for the new course, they didn't put these 3 on it. Sectan goes to sec. Probably more handy to remember that when you differentiate sec, you get sectan, but I mean, it's in reverse. And these ones here will certainly come in useful when we're handling what we call quadratic denominators. And they're very similar, you will notice. The only difference is the square root sign. Both of them become the log of x plus the square root sign, whatever is in the square root sign. I suppose technically there should be absolute values around them, but anyway. Okay, let's do some. X on the square root of x plus 4. Now you'll recall that in extension 1 that will give us the substitution usually. Extension 2, the difference is we have to come up with it. So I've got x times the square root of x squared plus 4. What's causing the problem? It's that square root sign that's causing the problem. Now I'm not suggesting you would actually do this by substitution, by the way. But if you wanted to, I would let u equal x squared plus 4. That's what's causing the problem. There it is. Well, that means du is 2x dx, and I can create that because I've got x dx. So I've got half of du. I can turn it into a half of 2x root x squared plus 4, which becomes the integral of u to the power of a half. Add 1 to the power over the power. Substitute back in for the u. I would not have left it like that. No, I did not. There's our answer. Of course, it's far quicker if you recognise the form of the integral. We talked about that yesterday. I see derivative times function to a power. I can simply go, okay, add 1 to the power over the power. If you spot that, it's going to be quicker. Or, here's another way I could have done it though. I could have done a different substitution. If you see a square root of a sum or a difference of 2 squares, that's what I've got here. I've got x squared plus 4. A trig substitution could work because our trig identities allow us to get 2 things and combine them to make 1 thing. So in this one, if I made x equal to 2 tan, then dx would become 2 sec squared theta, and I can just sub straight in now. So x becomes 2 tan theta. Square root of x squared plus 4 becomes the square root of 4 tan squared plus 4, and then the dx becomes 2 sec squared. Well, 4 tan squared plus 4 is 4 sec squared. The square root of 4 sec squared is 2 sec, and so I end up with 8 times tan theta sec cubed. I actually now have derivative times function because the derivative of tan is sec squared. Hang on, that leaves me with a sec. No. The function is the sec because the derivative of sec is sec tan. If you don't see it, move everything into sines and coses and it might become more obvious what you can do. So sine theta over cos. Sine is the derivative of cos. So if I wanted to, I could do yet another substitution. U equals cos theta. Du is minus sine theta to theta. Eventually I've got something I recognise. Du on u to the power of 4. Substitute back in, there it is, sec cubed. Notice how the function was the sec. That's what I was saying before. A lot of people would stop there because they're going, oh, u beaut. But remember, sec theta, I've got to get it back to x. How do I get it back to x? Well, we started with x equals 2 tan theta. So I'm going to draw myself a triangle. There's theta, opposite over adjacent, x on 2, hypotenuse. It is not a coincidence that the missing side of my triangle happens to be exactly the same as the square root sign in the question. I just read off my triangle now. Sec is reciprocal of cosine. So I have hypotenuse over adjacent. Sub that back in, and eventually I now have my answer. Is that the best substitution to use? Probably not. But it's another way. Remember, it's now your choice what you do. X times the square root of x plus 1. What's causing me the problem? But this time, instead of just making it what's in the square root sign, I'm going to make it the whole of the square root sign. I'm going to u equals the square root of x plus 1. In other words, what I'm saying is x is u squared minus 1, which means dx is 2u du. Let's now throw it in. So I've got u squared minus 1, that's what x is, over u, because I made u the complete square root, times 2u du, and very simple integral. Add 1 to the power over the power, sub back in. No way in the world I left it like that. There we go. Look at that. That's so much more fun. There it is. Of course, another way I could do this one. X times the square root of x plus 1. I could do an algebraic manipulation. Remember that idea I talked about yesterday? Create multiples of the derivative or the function itself. So I could rewrite this as x plus 1 minus 1 mod of the square root, split it up, bang. Ah, look at that. Add 1 to the power over the power. Bingo, there's the answer. So algebraic manipulation is the better way to go on this one. Let's do a definite one. Dx on 1 plus root x all squared root x. What's causing me the problem here? Well, 1 plus root x seems a logical substitution to use. U equals 1 plus root x. So du becomes dx on 2 root x. Yep, I've got everything I need. Limits. When x equals 1, u is 2. When x equals 4, u is 3. Let's change our integral. There it is. Du on u squared. There it is. I'm telling you, happens so often. Du on u squared. Never forget this. It's important to separate your variables before substituting. What do I mean by that? Don't do something like this. Dx equals 2 root x du, and then sub that in for dx. And you then have an integral which has both x's and u's in it. You haven't separated the variables out. You got to separate your variables. If your new integral is du, which is what mine is, everything has to be with respect to u. That includes the limits. So I've got to change those numbers as well. So back to that non-standard integral. Du on u squared is minus 1 on u. Substitute in, we have our answer. Ooh, a trig one. All right, let's just imagine for a sec that I don't see derivative times function here. What's causing the problem? Well, the trig's to the power of 5, so sine. I'll make u equals sine x. Du is cos x dx. Limits, got to fix those up. Root 3 on 2 and 1. Let's sub everything in. Nice little polynomial there, just u to the power of 5. Add 1 to the power over the power. Substitute in. We have our answer. X dx on the square root of 25 minus x squared. What's causing me the problem? 25 minus x squared. That's in the square root sign. So du is going to be minus 2x dx. Limits, let's fix those up. Oh, du on root u. What do you know? There it is. Well, du on root u, that's 2 root u. So we end up with just simply the square root of u. Square root of 16 minus the square root of 9. We have 1 as our answer. Square root of 25 minus x squared, go from 0 to 5. Well, what's causing me the problem? I'm going to do a trig substitution. I see a square root and a difference of 2 squares. Seems a logical thing to do. So x is going to be 5 sine u. That means that u is the inverse sine of x on 5. The reason I've done that is because I'm going to have to change my limits. That makes it easier for me to work out the limits when I see it in that form. Dx is 5 cos u du. So we end up with limits becoming 0 and pi on 2. Square root of 25 minus 25 sine squared. Well, that's 25 cos squared. Square root of 25 cos squared. 5 cos. 5 cos times 5 cos gives me 25 cos squared. Oh, cos squared. Double angles. So we've got half of 1 plus cos 2u. integrate that, excellent. Now, substitute in, I have my answer. Was that the best way to go? Nah. Let's do it this way. Draw a picture. Oh, we got to ask a semicircle. Oh, look at that. It's just a quarter of a circle. Oh, I could have just gone to quarter pi r squared. Oh, well, there you go. There's the answer. Remember, the idea of integration is to help us find things of unfamiliar shapes. When it's a shape we recognise, we have formulas that will work it out for us a lot quicker than integrating something. Okay, spot that. Oh yeah, how much time have I just saved by doing that? Okay, here we go. Remember, substitution is not necessarily given. Sometimes they will still give you the substitution, but not necessarily. A lot of the times they don't. You've got to work it out yourself.